In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 72. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with acid hydrolysis and oxidation reaction rather. Particularly in power transformers, the main constituent of solid insulations are cellulose-based and are used in distinct forms such as kraft paper and pressboard. So, the importance of maintaining the insulation performance is rather invariably dependent on the actual condition of cellulose structure and glycosidic bonds in cellulose chains. Cellulose-based insulating paper is primarily composed of several hundreds of glycosidic bonds. It is important to note that the average number of glycosidic bonds in a cellulose chain would have to quantify the number of repeating structural units within a polymer chain, which is referred to as the degree of polymerization of the cellulose structure. The degree of polymerization value of cellulose insulation paper is rather be directly related to the paper's mechanical strength and its respective withstanding ability to counteract all the crucial electrothermal stresses as developed during operational hazards. So, a higher degree of polymerization value for cellulose insulating paper would therefore signify a presence of larger number of glucose units linked together, resulting in a longer cellulose chains. In case of new unused cellulose insulating paper, the degree of polymerization value is typically found in ranges between 900 to 1400 glucose units or glycosidic bonds. The degree of polymerization value, while drops down to 200, that indicates the actual loss of capacity to support electromechanical tensions and becoming much more vulnerable to failure when the equipment is submitted to force due to short circuits. Now, the degree of polymerization value of cellulose insulation paper would have been dropped down as corresponds to the breakdown of glycosidic bonds in its cellulose part. So, the degradation mechanisms of cellulose-based insulations would have a direct relation with the degradation of glycosidic bonds of the cellulosic part. There are several factors which may have to influence the process of degradation of glycosidic bonds in the cellulosic part of the solid insulations. The gradual aging process of cellulosic structure of transformer paper insulation is rather to be accelerated by continuous breaking of glycosidic bonds on the cellulose chain under the catalysis of heat, moisture, oxygen and electric field, that is alternating electric field. The rate of hydrolysis of cellulose paper insulation in power transformers must have to depend mainly on water and acid. Acid formation that has to arise primarily from oxidation of the oil, oxidation of insulating oil that would have to occur during the process of chemical reaction as initiated between its organic hydrocarbon chain with oxygen and heat. Especially at elevated temperatures, the rate of oxidation would have been further accelerated, and that also leads to faster rate of acid formation. Mineral insulating oil, while used as transformer oil, that consists mainly of a complex mixture of different types of hydrocarbon molecules. Through the process of oxidation, these hydrocarbon molecules in transformer oil can indeed form hydrophilic, that is, water loving acids such as carboxylic acids. However, various byproducts that are to be formed during the process of transformer oil oxidation. However, various byproducts that are to be formed during the process of transformer oil oxidation. These include organic acids, especially fatty acids, carboxylic acids, water sludge, and various organic compounds like alcohols, peroxides, aldehydes, ketones. All these reactive oxidation compounds can contribute to the overall degradation of the oil and the insulation system. Carboxylic acids are thus to be produced by a series of free radical reactions involving peroxides and always have an affinity with cellulosic paper rather, and water due to their ability to bond with the hydroxyl group, OH group. Mineral oil based transformer oil is rather being susceptible to oxidation and hydrolysis, which thus to involve in formation of various low and high molecular weight carboxylic acids. It has been exhibited that the low molecular weight carboxylic acids like formic acid and acetic acid are comparatively much more hydrophilic than that of high molecular weight acids like naphthenic acids and stearic acids. Low molecular weight acids, specifically formic acid and acetic acid, that are soluble in water as well as transformer oil and prefer to stay in paper, which eventually affects the paper insulation. However, under the same condition, the solubility of acetic acid in mineral insulating oil would have been much higher than that of the formic acid and is even considered as the main component of acids generated during the aging of oil paper insulation in power transformers. Again, I repeat, however, under the same condition, that is temperature and other conditions, the solubility of acetic acid in mineral insulating oil would have been much higher than that of the formic acid and is even considered as the main component of acids generated during the aging of oil paper insulation in power transformers. So, it must be taken to understand that the low molecular weight carboxylic acids have the greater rate of influence on the process of paper degradation by acid hydrolysis, most important, and simultaneously involved in the degradation of oil itself, leading to the formation of insoluble deposits. Naphthenic acid and stearic acid both are considered to be high molecular weight carboxylic acids as formed due to the oxidation of transformer oil. Though these acids are normally not being directly aggressive to cellulose based solid insulation, but their presence can still affect the overall aging of the transformer insulation system. High acidity level, which includes both low and high molecular weight acids, would have always to indicate the oil degradation and potential problems with insulation. When the mineral oil is subjected to high thermal and electrical stresses, there would have been generated various combustible gases such as hydrogen, methane, ethylene, ethane, and acetylene resulting from decomposition of the oil molecules. At the event of electric stress developed within the transformer, that would also accelerate its aging process, which possibly by intensifying the precipitation of acids as produced from the oil degradation incidents onto cellulose-based paper surfaces. Formation of acids that would have the situation much more worsen as because those aggressive decay products which are being absorbed by the solid insulation would thus lead to affect the chemical and physical characteristics of its cellulose fibers. Breakdown of the cellulose fiber structure of solid insulation would have been resulted a loss of tensile strength of the paper itself. Catalytic effects of low molecular weight acids on insulation system of transformers. 1. Corrosion and degradation. A. Acidity would have to corrode the metallic components within the transformer. B. Degradation of paper insulation due to acid hydrolysis would cause to weaken the structural integrity of paper insulation, leading to reduce its dielectric strength, and that may ultimately increase the risk of failure. C. Acidity also contributes to sludge formation. pH balance. Presence of carboxylic acids in transformer oil can disrupt the pH balance of the paper insulation, ultimately leading to a decrease in the paper insulating properties. B. Decreased pH and increased acidity in the paper insulation can lead to further increase of leakage currents, partial discharge, which ultimately force to initiate breakdown of solid insulation, causing a potential failure of transformer. Hygroscopic in nature. A. Low molecular weight acids in transformer oil are hydrophilic in nature, so they have the greater affinity for water molecules and always have the possibility to readily absorb moisture from air. B. Increase of moisture level in transformer oil that would thus to further promote chemical reactions causing intensive degradation of cellulose-based paper insulation. And the last one and the most important one, that is electrical properties. Carboxylic acids are the polar compounds, and their presence in transformer oil leads to an increase in its dissipation factor, causing to degrade the oil's insulating integrity. B. The presence of elevated acidity levels that may instigate to partial discharges or corona formation within the transformer, which can further degrade the insulation over time and increase the risk of electrical faults. Now, aspects of aging mechanism processes of transformer paper insulation structure. 1. Thermal aging is the most prime and dominating factor. Again, I repeat, thermal aging is the most prime and dominant factor. Acid hydrolysis is one of the major contributors to the aging of cellulose-based solid insulations. Transformer oil that would also have to degrade over time due to formation of various acids with varying molecular weights. Oxidative aging is the process of cellulose macromolecular chain breaking. And the last one, electrical aging, is a complex process undergone by factors like heat, chemical reactions, and electrical stress. The primary cause to breakdown of glycosidic bonds in cellulosic part of the paper insulation is mainly because of some chemical reactions like pyrolysis that cause heat, hydrolysis that is moisture, and oxidation that is oxygen. That is, again I repeat, the primary cause to breakdown of glycosidic bonds in cellulosic part of the paper insulation is mainly because of some chemical reactions like pyrolysis when at elevated temperatures rather, hydrolysis that is presence of moisture, and oxidation presence of oxygen. Depolymerization or the breakdown of long cellulose chains would have to start occurring in cellulose insulation system while the temperature of the insulating system exceed the design values. High temperature that can initiate thermal reactions in cellulose insulation paper, causing an eventual breakdown of its glycosidic bonds, especially in the presence of moisture and oxygen. At high temperatures, there may have the possibility to occur thermal degradation through pyrolysis, where the cellulose would have been decomposed into simpler molecules. Even at normal operating temperatures, presence of moisture can accelerate hydrolysis of cellulose insulation. Most important. It has already been discussed that the cellulose insulation paper is susceptible to hydrolysis, which is a chemical reaction where the water molecules would have to involve in breaking the glycosidic bonds, causing to produce more water in the system. So, within the system, hydrolysis reaction would have then become an autocatalytic in nature, as because there would have to create a self-sustaining cycle of producing water till the process of cellulose breakdown continues. In a power transformer, the integrity of the paper insulation is the most crucial issue, which would have to depend on two common aspects. One, direct thermal degradation of the cellulose. Number two, self-sustaining cycle of producing water that enforces further hydrolytic degradation. Hydrolysis in a transformer once started to activate, then there would have a chemical breakdown of the cellulose structure within the insulation paper due to its reaction to water, and which in turn more water would have been produced as of a byproduct of the breakdown of the cellulose polymer chains. These water content as released would have to dissolve into the surrounding transformer oil, which not only reduces the insulation properties of oil but also accelerates the aging of the insulating oil. Transformer oil is, however, continually exposed to various stresses like mechanical, electrical, and thermal stresses, and oil is being gradually degraded by the occurrence of oxidation process. The oxidation of oil is a complex process, and that would have to contribute free radicals, that is electrically charged particles in chain reactions. Under the strong electric fields, these free radicals would have become much active to react with other molecules and thus to produce more decay compounds in transformer oil. The oxidation process of hydrocarbons within the transformer oil that can be carried out in multiple stages. 1. Initiation. 2. Propagation. And 3. Termination. At the initiation stage, the presence of oxygen in oil would react spontaneously to dissociate a hydrogen molecule, causing to form hydroperoxides, which again dissociated into free radicals. At the propagation stage, these dissociated free radicals would then to react with other molecules in the oil, causing to generate more free radicals, which then going to involve in a chain reaction that rapidly degrades the oil. Eventually, the oxidation reaction would have been terminated when stable molecules that are to be formed, which thus to act as non-reactive compounds and cannot react with the free radicals. So, the propagation stage where to perform these branched chain reactions would cause to act the major degradation of transformer oil over time. Now see the figure 196, principle of transformer oil oxidation reaction process. Transformer oil oxidation is a detrimental process where the oil molecules react with dissolved oxygen, involving electron transfer, especially the loss of electrons from the oil molecules. So, the oxidation reaction is an electron transfer process where the oil molecules would have to lose the electrons and become oxidized. Transformers in service condition, there would have several factors which are being usually involved in the degradation process of the total insulating system as provided. During a typical operating condition, the insulation system undergoes various reactions due to thermal and electrical stress in the power transformers. Now see the chart. Factors which affect the rate of oxidation of transformer oil. 1. Temperature. And overall high operating temperature of transformer oil that would always have to act as the most prominent oxidative accelerator. Oxygen. Oxidation typically involves the reaction of the oil with direct contact with dissolved oxygen, and that would have been accelerated at elevated temperatures, resulting in formation of various compounds like acids, sludge, and other byproducts. Moisture. Moisture or water content is one of the most significant contaminants in transformer insulating oil. It has been revealed that the chemical compounds of transformer oil are also to be affected due to the presence of moisture and temperature. Electrical stress. Electrical stress combined with temperature and moisture can lead to the formation of free radicals and other decomposition products which then participate in oxidation reactions in transformer oil. Contaminants. Several types of contaminants which include moisture, air, particulate matter and degradation products from the insulation itself would have to accelerate oxidation reactions in transformer oil. Particulate matter in transformer oil like metal debris or dust can act as catalysts for the oxidation process, leading to faster oil degradation and sludge formation. Let's stop here, further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share, subscribe. Your subscriptions would encourage to post more videos. Also share your comments, feedbacks. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.